As part of our last notes for this part of our class, we are going to talk about seafloor spreading. I will highlight the sections that you need to write in your notes. If you have the paper copy, it's fill in the blank. If you need to pause the video to get more time to write, please do so at any point. So, seafloor spreading. This refers to, fireworks. This refers to this area. Focus. There we go. This area here where the magma comes up from the mantle into the crust and it goes in between two plates. And as it does that, or in the middle of a plate, as it does it, it causes this trench here. And a trench is, the bottom. It's kind of like a hole. And it's at the sea floor. And it's pushing this plate this direction. It's pushing this plate this direction. And as it's doing that, it's spreading the sea floor. But instead of the world, the earth, getting larger, over here, this part of the plate is then going under the crust and recycled into the mantle. So let's put that into words. A mid-ocean ridge is the longest chain of mountains in the world. Scientists mapped the mid-ocean ridge using sonar. At the mid-ocean ridge, molten material rises from the mantle and erupts. The molten material spreads out, pushing older rock to both sides of the ridge. Youngest rocks in the ocean are at the mid-ocean ridge, and the oldest at the trench in the subduction zone. Seafloor spreading is the process where the new crust is formed at the mid-ocean ridge and destroyed at the ocean ridges, melting back into the mantle. So we are going to write all of this, but first I'm going to take you back and then you can pause the video. So let's see what it's talking about. So here is the ridge, the mid-ocean ridge. The trenches are over here. I said that backwards a minute ago. So here in the ridge, goodness, Miss Foster, in the mid-ocean ridge, it's in the middle of an ocean. It's pushing these plates this way due to convection under the earth. So you are going to write this whole thing, this whole slide. It is all important. The youngest rocks obviously are going to come in the middle because those are brand new. It's kind of like the hair on your head. It's going to spread from your roots to the tips. So the tips of your hair are much older than the roots. And this is the same thing. It comes, this magma is coming up here and it's pushing. And we see this mid-ocean ridge all the way across the world. So please pause this video and continue to write. Moving on. Evidence for seafloor spreading. New materials erupting along the mid-ocean ridge. The presence of pillow-shaped rocks has showed that molten material has erupted again and again. Oceanic rocks show that Earth's magnetic poles have reversed. Iron bits lined up in the opposite direction. And drilling into the seafloor shows the youngest rocks closer to the mid-ocean ridge, while the older rocks are further away. So we have physically drilled into the seafloor where it was relatively thin, and we're able to see this. They can take the rocks and do testing on them to see how old those rocks are. So what we have here in this pattern right there is in the very middle is the yellow young rock, and it's going to look differently than what's next to it because it's pushing out similar types of rocks. And then they are older on this end and this end, and it's causing it to be different materials. Now, what we do see is that the reason that we've colored them this way is that we're showing that there's normal polarity and then reverse polarity. If you were virtual, you would have seen in the last video how the poles have reversed, and we see it because of the way the rocks are stuck in this form. So the ocean floor has this stripe appearance to it because of that. So please pause the video and write this entire slide, and then continue when you are finished. Okay, let's continue on. Again, we're going to write this, and I want you to draw this to the best of your ability. So what we have here is the ridge push. It occurs when the new crust forms at the mid-ocean ridge, and it's pushing older crust away. So it's pushing it. It's pushing it this way, pushing it this way. Slab pull occurs when a slab of old crust gets pulled down by gravity at these trenches. So pushing up new rock, pulling down old rock. And the reason that they're going down is because they are more dense. Old rocks are more dense. Heavy plate sinks, pulling plates behind. Whereas the new stuff is more buoyant. It's magma that's being pushed up, and it's pushing those plates apart. So please write this and draw this to the best of your ability. Pause now if you need to. And then we're going to continue on. Again, writing this, the processes of subduction and seafloor spreading can change the size and shape of the oceans. Because of this process, the ocean floor is renewed about every 200 million years. So we have the convergent plate boundary, transform plate boundary, divergent plate boundary, all these types of plate boundaries. And what we're seeing is subduction along this area. Oceanic crust is more dense than continental, which means the oceanic crust is going to be pushed under the continental. Okay. We know that this is every 200 million years by testing the rocks, and we know subduction means to push under, so it's being subducted under the continental crust. We're going to write all of this again, so pause it if you need to. The Pacific Ocean is shrinking at an average of 9 centimeters a year, which is about 3.5 inches. This is due to the fact that the deep ocean trench is swallowing more crust than the mid-ocean ridge can produce. So it's kind of like it's losing weight. The Atlantic Ocean is expanding at an average of 2.3 centimeters a year, and we can see all of this from satellites in space. Please take time to read this again and then write it and move on to the next slide. All right, moving on. We see that we have no more of these slides, but I do hope that you watch the other video and look at these notes again for future reference, because this is what we call evidence of plate tectonics, seafloor spreading. So this is what we need to know for plate tectonics.